welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see about how to do the thermodynamic assessment in the Gibbs energy optimization itself. These are going to be the contents. We will see what are the variables we are going to optimize and the tool that we are going to use, and the target function, which is basically the sum of squares of errors, which is the one which is to be minimized to get the best optimized Gibbs energy, and that is done through iterative process. We'll see about that, and the exact procedure, the step-by-step procedure to be followed in the software, and a hands-on session doing the thermodynamic assessment or the Gibbs energy optimization part for silver copper system. Okay, the map is there in your mind, and this is where we are fitting statistical fitting or optimization. In the last class we have seen some guidelines for this. In fact, there are so many guidelines, but all of them could not be mentioned. As one starts doing thermodynamic optimization, one can start going deeper into all of them. I'll give the references towards the end of the course, and in this class we will see how to do the statistical fitting. Okay. An example model is given here, delta G excess mix, the simple RK polynomial kind of thing, where these different variables coming v1, v2, v3 and all, we called it coefficients when we introduced this idea, but in the Parrot module, which is the tool we are going to use in Thermocalc software, this will be called as variables, and these variables should get a number. That's the target now. So optimization procedure is to get the Gibbs energy description that best fits the input data, adjust model parameters in the Gibbs energy model of each phase. So each model parameter itself is built from one or more variables. A variable is single numerical value, and that's what we have to get for v1, v2 and v3. We have to get single numerical values for each of them. And optimization is an iterative technique employing non-linear least square methods, and this particular method is incorporated into the routines of this Parrot module in Thermocalc software. That's the tool we are going to use, Parrot module of Thermocalc software, and we have to use console mode for this. Target is to minimize the function sum of squares of error. Sum of squares of error is essentially this part, the experimental value minus calculated value. The difference between them is what we want to minimize basically, so that we get the best fit. But the error is quantified in this manner because these things also matter. The weight that we assign to each experimental value divided by estimation uncertainty. Okay, the standard deviation part that we enter for each value, so that will go in the denominator, the whole thing squared, so that we get sum of squares of error. And this thing should get minimum, therefore we get minimum difference between calculated value and the experimental value. Okay, this is where we are heading to. Okay, target is to minimize sum of squares of error. Steps during the optimization or this iterative procedure that we are talking about is, first there will be some start values for the variables. With that, there will be a forward calculation done. Okay, start values of variables are used to calculate phase equilibria or thermodynamic properties. That's the first step. We call it forward calculation. Once that is done, then error evaluation is done. Results are compared with input data. This is basically sum of squares of error. After that, the parameter update is done then as the next step, where in Parrot module, numerical non-linear least square methods are enabled, and they are used to tweak the variable, the values that are assigned initially. So now the variables are tuned based on this. The new variables will be used to do this forward calculation again, and the errors will be checked again. If the errors are significant, again the variables will be tweaked again. So this is repeated. That is the iteration. These steps are repeated until convergence occurs. That is, changes in parameters no longer significantly reduce the error, or the parameters themselves do not change much. Till then, we keep optimizing, and if the error doesn't come down, we say that doesn't converge, and if the error goes down to a minimum value and it doesn't decrease further and the value is acceptable, the error value is acceptable, then we can say convergence has occurred. That's where the optimization ends. Now a step-by-step procedure is here. This is known to you. Prepare the setup file and pop file with a text editor and run the setup file. Okay. So this part we have been discussing about this part. The setup file exactly we have not showed till now. Pop file, couple of entries how to make in pop file, we have discussed about that in the last class. Setup file I will show you today. The first step in procedure is to run the setup file where the models will be, and the setup file runs in GES module. This is Gibbs Energy System, that's the name of the module, and this module is used to basically define the functions with the v1 v2 kind of variables that is set up in this. Okay, but we don't directly go to GES module and type each syntax separately. We do all the things in setup file and run the setup file directly. So once that is done, we start the parrot module and create the work or store file which has this extension .bar. This file is created. This file we cannot see, but we can interact with parrot module. Parrot module will keep modifying things into this file. Okay, so this file is under the hood. Once this parrot module is started and par file is created, then we can compile the pop file inside the parrot module. Then what happens is the experimental data which is from this pop file will be stored on the par file. So that will come into this par file. Okay. So already model is there in GES. After running that setup file, we open the parrot module and create the par file and add all experimental data to that. So now everything is in par now. Models and the experimental data and the input data, right? Then select which variables to optimize and state start values, because we are not going to optimize all the variables together, taking all the input data together. We will select certain number of variables and we will assign some start values for them, which is basically usually done by the software as we discussed in the last class. Then go to edit experiment module. This is a different module. Now modules have highlighted in the yellow color. So go to edit experiment module and select the input data to be considered and set weight to them. By setting weight, we can select the input data. For others, we can set weight as 0. The input data that we don't want to be optimized at any stage, we can assign weight for them as 0. Then calculate equilibrium. This is the forward calculation we are talking about. With the initial set of start values, calculation will be done. And then save and go back to parrot. So now we will be in edit experiment. From there we'll go back to parrot module. In edit experiment, the job to be done is to assign weight to different input data and calculate equilibrium. Make sure that equilibrium is calculated. Once we are back to parrot, we can do optimizing. So we can the type optimize. Basically all these things in these capital letters are the syntaxes that we will be typing, are the names of the modules. Check results, list optimizing variables. These things we can do to check how the optimization is going. We can check the errors and see whether they are getting smaller or they are being constant. Those things we can check. Then we can rescale the variables to set the start values to the final value. So let's say we have optimized some 100 cycles, and then these initial variables should be initially in this whatever start values you have given. Then when we type rescale, what happens is the variables will get the final values that are obtained at the end of the optimizing cycle. So with this rescaling, we can again go for optimization if required. Then keep optimize and rescale until no significant changes occur. So once we are satisfied with the error levels, then fix the optimized variables and repeat for next set of variables and input data. So we have taken some input data and select which variables to optimize here. So some set of initial optimizing variables we took and took some input data corresponding to that and optimized. Now once that is over, then we can fix those variables and go to another set of input data and another set of variables to be optimized. Then go to GES, save. So once all these things are optimized, then we go back to GES module and save it. Therefore, the data that we have optimized will be saved, and now models will become descriptions now. Let's see the hands-on optimization. We are going to do it for the silver copper system. This is a very simple system where you see an FCC on one side. This is silver rich solid solution. FCC on the other side also, which is copper rich solid solution, and a liquid in the top. Three single phases we have in the phase diagram. But if you see the crystal structure, the left and right extreme, the terminal solid solutions, both have FCC structure. And we have been telling Gibbs energy curves or Gibbs energy models will be one model for one crystal structure. So we will be using one model to define both these FCCs. Therefore, now we are going to have only two phases as far as the models are concerned. It will be liquid and FCC. So two phases. The input file has thermochemical data, enthalpy of mixing in the liquid is available, and phase equilibrium data where these liquidus temperatures, all these pink line data, plus eutectic reaction, that is eutectic reaction here, liquid giving two solids, that eutectic reaction data, which is basically what is the temperature and what is the composition of the three phases in equilibrium. That data is also available. So this phase equilibrium data is available. So this is the total data availability. No activity, no more EMF or any other data is not available. With this, we are going to proceed with optimization. Optimization actually has been done because optimization is a quite involved procedure and it takes a lot of time. Even for a simple system, it takes a lot of time. Usually, if you see for a ternary or let's say a couple of ternaries, if one does the thermodynamic assessment, it becomes a full PhD problem. So it takes such involved work. So for this particular system, optimization has been done. So I'm going to take the optimization macro file where the set of variables to be optimized, what initial values, start values to be assigned, all those things have been tried out in different ways and some final shape has come. So that file I'm going to open and it is available to understand the process. So I'll keep that file on one side and open ThermoCAD and keep copy pasting the syntaxes from there to here so that you see how each syntaxes correspond to the optimization steps. Okay, the first step is to keep the POP file and the setup file which has this extension of TCM, both of them in a folder like this, and we can give such file names to them. I'll show you how the TCM file looks. Okay. You see, TCM file starts with Go Gibbs. Go Gibbs is go to GES module. Once we go there we enter elements. This is all the element data. Enter element vacancy, silver, copper, and then once the element names are entered, we can amend the element data with the unary properties. This is basically the atomic mass, enthalpy and entropy of these elements here. So silver, copper and vacuum, electron, gas, these things are entered here. Then we have this enter symbol function GHSCR AG. This is basically Gibbs energy of the pure silver. When we introduced about computational thermodynamics, we showed how the Gibbs energy database looks from 298 to 1234. There is a complex function for this particular GHSCR AG, meaning the silver's Gibbs energy is described like this in different temperature intervals. Right? Similarly, enter symbol function GHSCR CU. So the copper's Gibbs energy is also entered. Both are with respect to the HSCR, meaning the standard elemental reference. And then we have G liquid AG. This is silver's liquid state property and this is copper's liquid state. So this unary data is also entered. So no more data from SGT is entered here. No BCC silver, no BCC copper, etc. Because only these things are relevant for this particular system. So we have entered only FCC data and liquid data. So that is about the unary. For the binary, interface liquid is entered here, and for liquid only one sublattice is chosen, Ag comma Cu, and this is how the liquid's Gibbs energy is described here. Enter parameter G liquid, which is basically G liquid Ag, which is described in the top, and G liquid copper is G liquid copper here, which is also described in the top. They are called here, and these are the things which are important for the binary Ag comma Cu. This is where the mixing terms are entered that have this V1 V2. You see, now we know the unary property from SGT, we are directly entering it. For the binaries we need to optimize. So V1 V2, V3 V4, V5 V6 are chosen. You can recall the LAB parameters 0, 1 and 2. These are the things here entered. This is for the liquid. Similarly for FCC, two sublattices with occupancy 1 and 1. So that is Ag copper in bracket, and the subscript is 1. Then vacancy in the second sublattice with the subscript 1. That's what it means when we enter 2 1 1. The sublattice formalism. Once we have that, then we can have these different mixing terms coming in. Okay. So the parameters are entered here: copper, silver, copper mixing. All this mixing happens in FCC. Again, we have three different L parameters. That's all. Only two phases we are optimizing: liquid and FCC. Is one of the simplest of the systems. So we have selected this. Once these things are entered, we'll be still in the GES module, because in the top we typed go Gibbs, and that's where we are entering all these things. Once all these functions and parameters are entered, we can go to parrot module, where we create a new store file. Okay, this store file AGCU will be the name for the parrot .par file that is created here. So this is syntax to create the store file AGCU. This is the par file creation, that is also named AGCU, and then compile experiments AGCU. This is the name of the pop file AGCU, and this will be compiled into this par file. Once it is done, we can go for further steps. There are many more smaller options which I am ignoring to teach now. Once it is done, all these models can be saved. Then further optimization can be started. Let's see how to do that. Okay, now we have a thermocalc window here, the console mode window, and in the right side we have a opt file, optimization, the macro file used for optimization, opt.tcm. This file is something that carries all the syntaxes, the right syntaxes used, the right values assigned to optimize it, because this has been created over a period of time, and since I am teaching you this in one class, I am using this file and going to show you what things were used to do the optimization straight away. Right. So first thing is, before using the syntaxes in this, we have to bring the setup file here. Let us type macro m is enough, enter. This folder AGCU opt is set as the default folder now. Therefore, this AGCU file can appear there, agcu.tcm. I am directly loading that. Okay. So whatever file that I showed you has now run. Okay. And a parrot file is created now, and we are in the parrot workspace now. So here we can start using the syntaxes that are typed here. Okay. Set optimizing variable 1 minus 10,000, set optimizing variable 3 minus 10,000. Okay. You have seen multiple V1, V2, V3 options, right? So we are now taking V1 and V3, only these two variables. Okay, and these two correspond to enthalpy data. Okay, so these are the start values of the enthalpy data we are giving, and we are going to load now the corresponding enthalpy values from the experiments, that is in this edit experiment module. So we have to go to edit experiment and read. Once we do this, what this edit experiment does is, from the compiled experimental data from the par file, it will read all the experimental data entered, and then we can type the set weight 0 for first to last, and then set weight 1 for 2 to 14, meaning first we are making everything 0, the weightage of all the data to be 0, and then we are giving weight 1 to the data of 2 to 14. 2 to 14 data entered in the pop file. Let me show you the pop file. Okay, this is the pop file where thermochemical data is entered, enthalpy of mixing for liquid, table head as I told is started, and enthalpy of mixing values are entered here with the error, 5% error for various compositions. These are the compositions, these are the enthalpy values. Similarly, we have the liquidus data here, liquidus temperature. So for different compositions, what is the liquidus temperature, that is entered here, and invariant reactions one eutectic reaction is there, the eutectic reaction data is entered here. I showed you in the last class how these things are entered. So in this you can see what is the number assigned, table head 2 here, meaning starting from this one, the number of experiments 2, 3, 4, 5 and so on. These are the number of experiments. So these two tables are here for enthalpy of mixing values. Those values will be used now for optimization initially. So let's go back to the opt file. So this is the opt file where we have this entire set of things, that is set weight 1 for 2 to 14, and then select first is start from the first equilibrium and compute all in the sense compute equilibrium for all the entered equilibriums in the pop file. So it will do that. Once it is done, calculation is successful, we can save it and go back to parent module. This is save and back. Okay, so we will copy from this edit experiment till this back, Control C, and here the mentoring, I'm pasting all of them. Yeah, now all of them are here. Yeah, you can see. So compute all we have given, setting weight 0 first to last, setting weight 1 for 2 to 14, and select from the first and compute all. So this is the result of equilibrium calculation for all. You can see here 1, 1, 1 is there, that's the weight assigned for 1 to 14. Other things are assigned weight 0, so they are displayed as unused, other experimental data. The liquidus and the eutectic reaction data, all these things are unused. This is our first set of input data and the first couple of variables to be optimized. So let us start the optimization. We have to type this one, opt 0 first, opt 0, enter. Okay, so now it has optimized. One step of optimization is done, that is the opt 0 step. Once it is done, we can type opt 100. This stage, make sure that there is no error. Okay, opt 100, enter. So now it does 100, this 100 optimization iterations are done, and you can see the sum of squares is 3.3 into 10 power 0. Okay, so now it is done. Then the rescale is done here. Rescale is done basically to change the initial values of optimizing variables to the newly optimized values. Type rescale. Again do the opt 100. Opt 100. Okay. Once again enter. So now optimization, one more cycle, one more set of 100 optimization cycles are over. Then again rescale, optimize. So if you keep doing that few times, list all variables. If I show you, this is what you see, V1, V3, these values are the ones we got now. Okay. So number of variables 2, they are being optimized. Now we can go to edit experiment and set weight 1 to 5 to 55 and select first, compute all, save back. Okay. Same thing we have done for those first set of data. We are going to repeat it for one more set of data. You can see 1 is assigned for all these liquidus points. Okay, so we have done that. Now go back to parent and give initial values, start values for a different set of optimizing variables. Okay, 3 optimizing variables, 2, 7 and 8 are chosen. So this will be optimized now. Okay, along with those in the previous step, choosing more variables along with the first set of variables, so that all of them will be optimized now. Okay, we are not fixing the values of the first set of variables because they are not satisfactory. We will see by adding more variables and more experiments, can we get better convergence. Okay, so that's what it is. So this kind of thing is repeated again. So I am just copying it up to, I am copying it up to here. Okay, so now you can see sum of squares of error is significantly less. Okay, at this point in time the variable 3 is fixed as 0. Okay. At this point in time you may not know why this particular thing was tried at all, because once you keep doing this optimization you will realize what variable is causing a lot of problem and how to and which one to be fixed at what value, all that you can design and proceed. Okay. So you can see then again optimization is continued, then more variables and more data, then more data is selected, okay, and more variables are selected, set optimizing variable 3, 9, all those things are taken now. Okay. So I'm copy pasting the entire file now. Right. So you can see here sum of squares is 1.8 into 10 power minus 1. This is significantly less, and it's reasonably okay. With this, if we see the phase diagram coming well, we'll stop there. Okay. So how to do the phase diagram? We will have one more file. We'll have one more file. This is a file to plot. We can open a new console here. Okay, and in this console we can go to Gibbs and read PD. The PD is the file that we have saved at the end here. If you see at GES we have saved a file called PD phase diagram, and this is where all the data is saved, and it is in the Gibbs GES module. Therefore we'll go to Gibbs module and read that PD file. Once we read that, it's like we go to poly module and then do the calculation. Okay. Just like the phase diagram calculation steps, we are going to use all of them. So we can simply copy these thing, copy these syntaxes, go to console mode 2 and paste it there. I minimize this window. The results console is here where you see the silver copper phase diagram has come, the one that I showed you in the slides. If you right click, add label and see FCCA1, FCCA1. Okay. This hash2 here is basically a composition set. Within FCC phase, now we have two different compositions, one copper rich and one silver rich. So composition sets can be created for that. In the TCM file, there was a provision just above the FCC. If you see, it is typed, but we have not gone deeper into that. But this is possible. And at the top, we have liquid phase. Okay. So this diagram is reasonably the one that we have been looking for. The melting points are more or less reproduced correctly in the eutectic reaction. So we can compare this directly one-to-one with the experiments. Even here, we can create a file called .exp file, an experimental data file that can be created and appended to this diagram so that the experimental data points will be superimposed. And that will give you a lot of insight about where what is going wrong, which data is not optimized well. That idea we can get and then go back to optimization again. As I told, I'm doing this kind of optimization is a very involved process. It takes at least few months to few years time. You have to have real patience and perseverance to do this. Thank you. I hope the lecture is useful. See you in the next class.